All right, welcome. Today is Chapter 4, Section 3, Finite Fields. It's an exciting section. Fields, as you know, are things that generalize objects like the real numbers or the rationals. And you would think that you would have an infinite variety of finite gadgets that acted like the real numbers. But in fact, it's very, very limited. And we can write down all of them, and we'll do that in this section. All right, to get going, we're going to need a definition. So here we go. Okay, start with the ring R, and we'll let I be all the integers k that kill everything in your ring. All k so that kr is equal to 0. It's obvious this is an ideal, and since z, this is an ideal in z, of course, and since z is a PID, and the units are plus or minus 1, then there's a unique k that's bigger than or equal to 0 that generates this ideal. Okay, that's that. Pick the k that generates the ideal. That's non-negative. We'll say this unique k that generates the killing ideal is the characteristic of R. As an example, let's start with z. Of course, the characteristic of z is 0 because the only number that multiplies everything to 0 is 0. And of course, if you look at z mod n, then it's easy to show that the only integers that multiply everything to 0 are multiples of n, and so n is the generator of that ideal. So the characteristic of z mod n is n. Okay, first theorem. Go ahead and start with a ring with identity. Okay, the first statement is that the ideal generated by 1 in the ring R is either a copy of z, and that happens when the characteristic is 0, or it's a copy of z mod n when the characteristic is n. And so after relabeling, we either get a copy of z inside of your ring or a copy of z mod n inside your ring, depending on the characteristic. Okay, part 2 of the theorem. We care about fields here, so let's assume we have a field. Then its characteristic always has to either be 0 or a prime. Now, in the case that the characteristic is 0, part 3 of this theorem says that, in fact, again, up to relabeling, a copy of the rationals sits inside your field. Part 4, if the characteristic of f is a prime p, then z mod p sits inside your field. Of course, we've already said that in part 1, but oh well, let's write it again. And then the final part of the theorem. If the size of the field is finite, then the characteristic has to be some prime p. And this is going to give us sort of our entry point to classifying all these fields. Obviously, this will follow from 3, right? Because if it were 0, then we would have to have the rationals, and that's obviously infinite. All right, these proofs are all pretty easy. Let's go ahead and get started. Okay, for the proof, let's prove this claim first. The defining ideal for this characteristic business was the set of all k's that killed everything. And the claim is that that ideal is the set of all k's that just kill 1. If you can kill the identity, it's the same as killing everything. So these are two sets. We're going to show that both are contained in each other. Obviously, the left-hand side is contained in the right side, so we need the opposite direction. All right, for the reverse inclusion, we know that k kills the identity in R. We want to show it kills everyone else. So the trick is to write kr to stick a 1 in there. It's k times 1 times R. And if you think about how this works, just factor, you've added the 1 times R k times, factor the R out on the right, so that'll be k times 1 times R. And then k times 1 was 0, so that's 0 times R, and then that's 0. So that's the proof of the claim. All right, let's turn to part 1. Define a map phi that goes from the integers to the ring just by multiplying the identity. So k gets mapped to k times 1. All right, clearly this is a homomorphism, and the range is just the ideal generated by 1 here. As a result, we get Z mod the kernel of this map is isomorphic to the ideal generated by 1. But as we've seen in this claim at the beginning, this kernel is exactly the ideal generated by the characteristic. So that's it. Part 2. If we're dealing with the field, then of course there are no zero divisors. That means if there are no zero divisors, then we can't get a Z mod n appearing as the thing generated by 1. Unless, of course, that n happens to be prime. So that's that. Number 3. Well, if we have an infinite a field with characteristic 0, then we have a copy of Z in it. We've already seen that's the ideal generated by the unit of the field. But it's easy to see once you have this, of course, you have all the inverses in here. And it's trivial to show that, in fact, you get all of Q. I'm going to skip that, though. All right, you can see that in your homework. Number 4, we already did. That was just a repeat of number 1. And number 5 we did already as well, because if you're a finite field, then you can't have a copy of Z, let alone Q, in you. And therefore, the characteristic had to be P. All right, that's it for our first theorem. We can actually get a little bit more from this, so let's see what happens. This will be a corollary of it. It's just a little bit more work, but let's assume we're looking just at finite fields, so say F is finite. We're also going to let P be the characteristic of F. We know it has to be prime. All right, then we actually can say a lot about the actual size of F. In fact, it has to be a prime power, some P to the n, where n is the degree of the extension of F over Z mod P. Remember, characteristic P means you have a copy of the field Z mod P inside of you. So the degree of that extension is the power of P. And this is already incredibly limiting, and you would still think there might be lots of fields with the same order, because that happens with most things. However, it's going to turn out this is the only invariant that you need to know for fields. We'll show in a little bit, actually, for every prime power, there is a field with that order and only one. All right, let's turn to the proof of the corollary first. So start with our copy of Z mod P sitting inside of F, and I claim that F has to be finite dimensional over Z mod P. If it were not finite dimensional, it would have at the very least an infinite number of basis elements, which is too many. It can only have a finite number of vectors. In particular, it can only have a finite number of basis elements. So in particular, it's got to be finite dimensional. So that n, the degree of F over Z mod P, is in fact finite. All right, so finite dimensional vector space, pick a basis, alpha 1 to alpha n, a basis for F over Z mod P. Well, equivalent to the definition of a basis, that means every element in our field is a unique linear combination of these alphas, where the coefficients can be in Z mod P. So every choice of coefficients gives us an element of F, and it gives it to us in one way. So you just have to count F, you just have to count how many combinations you get here. But you have P choices in front of each alpha, so you end up with P to the n elements in your field. And that's the end of the proof. All right, let's see if we can cook up an example here. What we've seen so far is that any finite field is an algebraic extension of Z mod P. So at worst, and a finite one. So at worst, we just have to attach a few algebraic elements to go from Z mod P up to our field. That sounds a little hard at first, so maybe let's try to look for fields where we only have to attach one element and see what we can get that way. All right, looking for all fields. Initially, let's look and see if we can get fields by attaching just a single element instead of a whole string of them. Now, secretly, it's going to turn out that you can always do this. That'll be part of the content of our next theorem, that you can always construct these fields by attaching a single algebraic element. So this first stab that we're trying looks as if it's very special, but it won't be. It'll actually turn out to be sort of the general case. All right. If we're attaching just a single algebraic element, then we know that up to isomorphism, it always looks like this. Because we know that attaching a single algebraic element is like going to the polynomials, zp of x, modded out by the minimal polynomial, and the minimal polynomial is irreducible, that means the fields have to look like zp of x, mod out some irreducible f. And then remember, we had this whole story in these cases with coefficients in a field that this f is irreducible. Then since this here is a UFD, it's actually prime. And then since it's a PID, it's actually generates a maximal ideal. And since it's a maximal ideal, then this thing is always a field. So this gives us a procedure of actually trying to construct these finite fields. Just start z mod zp of x, mod out by f. As long as f is irreducible, then this quotient is one of our finite fields. And as I said, it'll turn out you can always succeed by this type of procedure. And as we've said before, these polynomials in z mod p, in general, saying whether something's irreducible or not is hard. But in any particular case, especially over a finite field, over a finite field, because you can just try everything, these questions of irreducibility are always easy to decide. Okay, I should add this as well. We even know how big this field is, because the degree of the extension when you attach this algebraic element was just the degree of the minimal polynomial. So the n from the previous corollary is just the degree of f. So whatever the degree of the polynomial is, then the size of this field is p to that degree. So it turns out this makes things super explicit in any particular case. Let's look at a concrete example. Okay, our assignment is to find a field of order 4. So you should factor 4 as 2 squared. It has to be a prime power, remember, if you're looking for a finite field. And so this base 2 here tells us we should be looking at polynomials with coefficients in z mod 2. And this exponent here says we just need to find an irreducible polynomial of degree 2. All right? Looking for an f that's in the polynomials with coefficients in z mod 2 that's irreducible and has degree 2. Now these you've done in lots of homework problems. You know the only possible choice there is. Here it is. It's f is 1 plus x squared. All right, so that's the only irreducible one of degree 2. Therefore, we have a field of 4 elements. F defined as z2 of x mod f, where f is this particular guy here. Now, actually, you can multiply and add in this field really easily. So let's do an example of that. Okay, officially, this is a quotient of a polynomial ring, so I should really write the field elements as 0 plus f, 1 plus f, x plus f, 1 plus x plus f. And remember, I don't have to go to degree 2. This is the entirety of the field. We said there were 4 elements, and there they are. But no one keeps this ideal generated by f. Instead, we'll just omit it and have to mentally keep track of it. So let me rewrite it. Okay, that's a lot shorter. F is just 0, 1, x, or 1 plus x. Those are the only 4 elements. Now remember, these are really representatives of cosets, so it's not a unique way to write them. For instance, 0 is the same as 1 plus x squared. But let's say we want to multiply. Okay, what is x times 1 plus x? Well, as you know, when you multiply in a quotient, you multiply the representatives. So you get x plus x squared, and that has to be one of our field elements, but it doesn't look like it's on the list. And that's just because it's a different representative for the coset. So remember, there's a plus f in there, and in particular, we can add any multiple of 1 plus x squared because that's 0. So in this case, I added two ones, and two ones is 0, right? So I didn't change anything. But then because this thing is 0, it's just 1. So in fact, x inverse is 1 plus. Anyway, if you wanted to make a multiplication table of all the products and all the sums, it'd be super easy using this sort of trick here. So you can work with these finite fields very concretely once you realize them as this quotient. And for the quotient, you just need to come up with the right degree irreducible polynomial in polynomials with coefficients in some z mod p. All right, so we still have to prove this big theorem that says all of this is legal. Okay, so let's start with the prime p in any natural number, at least 1. Part 1 of the theorem says that up to isomorphism, there is a unique field so that the order of that field is p to the n. So it's both existence, there are always fields like this, and uniqueness, just one. It's only a single field. There are two main conventions for writing this field. One is f sub pn. That's how I will always write it. There's an older notation written gf of pn that stands for Galois field. Anyway, that's part 1. Part 2 identifies the first way of how to construct a field like this. It says all you have to do is start with this polynomial x to the p to the n minus x. So that's a polynomial in zp of x. Grab its splitting field, which we know exists from a previous section, and that is the field of p to the n elements. This construction is very useful for most of the theoretical things we'll do, though it's not as helpful if you actually want to work in the field. All right, part 3 gives an alternate construction useful for actual calculation. All right, so, where are we? Oh, so you can also construct the field of p to the n elements as zp of x mod q, where q is any irreducible polynomial in z mod p of x of degree n. And a corollary of this theorem will be that such irreducible polynomials always exist. Of any degree, there's always an irreducible polynomial there. All right, and finally part 4, though of course 4 will come before 3 when we prove it, is to note that the field of p to the n elements is always a simple algebraic extension. So just an amazing theorem. All right, let's get to the proof. Let's start with 1 and existence. We'll actually do 2 along the way, but existence actually takes the most work. And it's a very clever argument. Go ahead and start with this polynomial that we claim is going to control everything. The f, it will be x to the p to the n minus x. Let's write f for the splitting field for f over z mod p. And we believe, of course, if we believe the statement of the theorem, that this will end up actually being the field with p to the n elements. But we don't know that now, but we do have it as a splitting field. All right, let's start with the little bit of calculus we do in this class. Let's take the derivative, f prime. The p to the n comes down. P is 0, so the derivative is minus 1. This doesn't have any roots, so in particular f can't have any repeated roots. So in particular, all the roots of f are simple, which means they're all distinct, so they're actually p to the n roots. All right, so label them in any order, alpha 1 to alpha p to the n. Those are the distinct roots of f. They're p to the n of them. And we know since f is a splitting field, it's actually z mod p attached those roots. Okay, here is the surprising claim. The claim is that actually, if you just list these roots, that's the whole field. That's already all of f. And if we prove this claim, then of course, well, f is a field, and manifestly as p to the n elements, so we constructed a field with p to the n elements. So we just have to prove that f is just those roots, and that's all there is. Okay, let's look at the claim, try to prove it. Let R for roots be just the collection of roots, alpha 1 to alpha sub p sub n. p to the n. We want to show that actually r is equal to f. Okay, now I claim actually we just have to prove two things. First of all, I claim we have to show that z mod p is an R, and then secondly, that R is a field in its own right, which just means we have to show it's a subfield of F. Because if we show that, then it's an extension of z mod p, and it's obviously the smallest extension that has the roots of F, because, well, it only has the roots of F. It's obviously the minimal one. And since it's the minimal extension of z mod p that has the roots of F, all the roots of F, then it is the splitting field. And that will give us that R is equal to F. All right, let's start by showing that z mod p is contained in R. Okay, this argument's pretty easy. Take any element in z mod p. Fermat's little theorem says z to the p to the n takes you back to z. That's the same as saying z is a root of f, and if it's a root of f, it's one of the alphas, therefore z is in R. So that one was simple. Next we need that R is, the set of roots are themselves a subfield. This is going to require a trick, and the trick is one actually you've seen in your homework, and it's the Frobenius endomorphism. All right, the definition is this: phi sub Frobenius will be a map from F to F, defined by just doing the pth power. Okay? Now, to do anything with this, we first need to observe that p divides this binomial coefficient, p, choose k, for k anywhere except at the extremes. And if you just write this out as the factorial definition, p factorial all over k factorial times p minus k factorial, you can see you've got a p in the numerator, and then in the denominator everything they're factorials where the top thing is always smaller than p, and so you just get smaller numbers, and by the prime factorization you'll never get that p canceling out in the denominator, so that p will always survive. So if you use the binomial theorem, which expands x plus y to the p as a sum with binomial coefficients, all the middle binomial coefficients, since we're in characteristic p, where p is 0, they all die. And so you get x plus y to the p is x to the p plus y to the p. This actually works always in characteristic p by the same argument. This is sometimes called the freshman's dream because you see this so often in your calculus classes that people think, x plus y squared is just x squared plus y squared, and don't ignore the middle terms. And it's true if you work over characteristic p. Okay, rewriting that in terms of the Frobenius endomorphism, we see that it splits up sums. The pth power of a sum is just the sum of the pth powers. And of course, it's obvious that it splits up products. And the result is that the Frobenius endomorphism is a homomorphism. Okie dokie. Next, since we have a field, there are no zero divisors, so the only way you can take something and raise it to a pth power and get 0 is if you started with 0, so just pull off c times everyone else. So this says that the kernel of the Frobenius homomorphism is 0. In turn, this says that the Frobenius homomorphism is injective. This says that the size of the image is the same as the size of what you started with. But if the size of the image is the same as the range, that means it's surjective. And so finally, if it's surjective now, then it is actually an isomorphism. So in this case, it's the Frobenius isomorphism. Now, oddly enough, this tool will let us check that the set of roots is actually a field. What do we do to have to check that it's a subfield? Well, we just have to show that it's closed under addition, closed under multiplication, and that all the inverses are there. Okay, so given any two elements that are roots, we need to show their sum, difference. stay inside the field, that their products do, and that their inverses do. All the arguments are kind of similar. Let's do the hardest one. Well, before we do the hardest one, to show that they're still in R, we just have to show that they're still roots of f. And to show the roots of f, we need to show that they're p to the nth power leaves it alone. But the pth power is just the image of the Frobenius map. To get the p squared power, we would do the Frobenius map twice. So to get to the p to the nth power, we would just have to do the Frobenius map n times and show we get back to where we started. Okay, so that's what I wrote here. We just have to apply the Frobenius map n times and show that it leaves each of these people where they started. All right, let's look at, say, the sum. Why should the sum of two roots be a root? That's the weirdest looking one, I think. We have to apply this Frobenius map n times. That means we do the pth power, then the pth power, and the pth power, and the pth power. We just use the fact that it is a homomorphism. So when we do the pth power, we can apply it to each term individually, and then again and again. So if we do this, we get alpha I to the p to the n plus alpha j to the p to the n. But alpha I was a root, and alpha j was a root, so its p to the nth power is back to where it started. So I just get alpha I plus alpha j. And so you see it was fixed, and that does it. You can do each of these cases up here by a similar argument. It's very simple. But the result is that actually these roots form a subfield, so they are a field, and that will finish the existence part. So that's the hardest part. Done. All right, we still have the we still have the uniqueness. Okay, so suppose we have possibly a different field, f prime. It's an extension of z mod p, because z mod p sits in there. And suppose it has p to the n elements. Then, in particular, since f prime is a field, its units, f prime super x, is everything but 0, so that has p to the n minus 1 elements. Well, since f prime sub x is a group under multiplication, that means c to the order of that group always takes you back to the identity for any c in the set of units. So multiplying both sides by c, c to the p to the n is always c for all c in f prime of x. And then the only person who was left out was 0. 0 obviously satisfies that equation as well. So in fact, for every element in f prime, c to the p to the n is equal to c. In turn, this means, well, that every element of f prime is actually a root of that polynomial f we started with. And of course, clearly that means f prime is a splitting field for f. And so that does the uniqueness, because we proved that every splitting field is unique up to an isomorphism. In fact, they're isomorphic by a z mod p isomorphism. Okie dokie. 2, we already... In fact, that's how we got existence. We showed that it was, in fact, the splitting field of f. Let's do 4 next. Okie dokie. F cross is a finite group, and it's a field. Well, it's sitting inside of a field. Therefore, we had that great theorem in the last chapter. That means it's actually cyclic. Let's go ahead and write alpha for the generator as a group for F cross. Okay, well, my goodness. If you can generate everything with just powers of alpha, clearly F is just z mod p adjoint alpha. All right, that finally leaves part 3. Let's go ahead and let Q be the minimal polynomial for alpha over z mod p. Go ahead and note that the degree of Q actually has to be n, because the size of the field is p to the n, and as we already said, the degree of that extension is that n. So we see that f, which is z mod p attached and alpha, is isomorphic to zp of x mod the minimal polynomial. The converse, we already mentioned before the theorem, that if you do this construction, zp of x mod an irreducible polynomial, then you get a finite field. So that'd be the converse there. Anyway, that is the end of the proof. Really great theorem. And the end of the section.